Hello everyone, this is my great pleasure to introduce Xiaoan Dong. Xiaoan is a PhD candidate from University of Rochester, and today she's with us talking about her past works on protection and efficiency of memory management systems. Yeah.
Thanks for the introduction. Hello everyone. For this talk, I'm happy to share with you my works about address translation efficiency and protection. First of all, I would like to spend a little bit of time introducing myself. My past research focuses on memory management at the operating system level, including two directions. One is about improving code, virtual to physical address translation efficiency of desktop, server, and mobile applications. I have explored several OS level approaches, including sharing page table and TLB entries for different processes, automatic superpage promotion for large main executable, and padding small code so that they will be able to use superpages. And the other direction of my work is about defending against privileged side channel attacks launched by compromised OS. I have designed and implemented defenses against page table and last level cache side channel attacks launched by compromised OS on the trusted execution environment. I have also evaluated the existing defenses, their performance. The existing defenses against bounce check bypass attack, Spectre variant 1 launched by compromised OS. For this talk, I would like to focus on two projects. The first one is improving code virtual to physical address translation efficiency of Android applications by sharing page table and TLB entries for shared libraries. And the other project, I would like to talk about defending against page table and last level cache side channel attacks launched by compromised OS on the trusted execution environment. So, starting with the first one, improving code virtual to physical address translation efficiency. The first question we may have is, why code address translation efficiency? It is because the code virtual to physical address translation overhead is already a performance problem. Across the desktop and server applications we have tested, up to 15% of the execution time is spent on servicing instruction address translation. And this is due to the increasingly large and complicated code base of modern applications. So first of all, modern applications, they have larger and larger main executable. For example, Clang is as large as 56 megabytes. And secondly, modern applications tend to use a lot of shared libraries. For the desktop and server applications we have tested, around 13 to 20 shared libraries are linked. And for the mobile applications we have tested, 88 to 107 shared libraries are linked. And for the first part of the talk, I'll focus on improving code virtual to physical address translation efficiency of mobile applications, in particular Android applications. Here's the outline of the first part of the talk. I'll start with introducing the current memory management mechanisms with a focus on shared memory. Then I'll talk about the Android code access pattern. What is so special about it? Why the current memory management mechanisms is not efficient for the Android processes. Then I'll show you our techniques, sharing page table and TLB entries. So, regarding the current memory management mechanisms, it is pretty common to see shared memory, like shared libraries, shared anonymous memory. Although only one copy of the physical memory exists in the system, each process still has its private page table and TLB entries. Even if the address translation information is entirely identical, then there will be duplicate address translation information in the system. And this duplication grows linearly with the number of processes and the number of translation entries. In addition, this duplication is all over the memory hierarchy, including shared caches, since a page table walk on the TLB miss will load the page table entries into the shared caches as well, displacing other useful data in the cache and degrading the overall performance. And there's a lot of duplicate address translation information on Android platform due to the special process creation model of Android. So Android has a special process called the zygote. It is responsible for initializing the environment. And one thing it does is to preload all the native shared libraries, the .so files, common to typical Android applications. And every Android application is a child process of the zygote process. So they inherit the virtual to physical address translation information of this preloaded shared library from the zygote. So when they start up, they don't need to load those shared libraries all over again. And the figure on the left shows an example. So we have zygote. It preloads libc.so, libart.so, and libm.so. Then later, over the course of execution, it forks crom and the Adobe Reader. And they inherit the virtual to physical address translation information for the preloaded shared libraries from the zygote. And later, each of them load their specific shared library upon the virtual address space inherited from the zygote. So crom loads libcrom.so, and Adobe Reader loads libadobe.so. Therefore, as a side effect, the virtual to physical address translation information of the preloaded shared libraries are identical across all Android applications, resulting in duplication with the current memory management mechanisms. So, in order to reduce the duplication, our goal is to share the page table and TLB entries for the preloaded native shared libraries across all Android applications. And our techniques is implemented at the operating system level with existing hardware support so that it is mostly machine independent. And the benefits of sharing page table and TLB entries include, firstly, reducing the number of soft page faults, which means that the physical page is already in the main memory, but the address translation is not. So it's cheaper than the real page faults. And by sharing the page tables, any page table entry populated by one sharer will be visible to the other sharers in the system so that they don't need to encounter soft page faults any longer. Yes?
When you say you want to share page table entries, do you mean you want to have multiple processes sharing the same actual portions of the hierarchical page table?
I mean, multiple processes will share the same leaf level page table page, the entire page.
Okay.
And I'll have a figure for it.
Okay. I'll hold my thoughts.
And
doesn't this break ASLR pretty badly? I mean,
actually,
I get that Zygote doesn't run ASLR. Maybe that's a problem.
Yes.
Zygote, but...
Yeah, so it already breaks ASLR. Okay. So yeah, that's true. So on Android.
Sure.
Yeah, but we also have other techniques on x86. It's more general. In that case, yes, it breaks ASLR, I admit.
Why do you think it breaks ASLR?
Well, sort of very fundamentally, because you've got two different processes that share the same V address, go to the same physical address.
Windows does that.
So hang on. ASLR can be per machine,
yes,
which is how Windows and Linux do it for efficiency reasons.
I mean, okay, per processor ASLR.
But it does break per processor.
Yes, yes.
Then also by sharing page table and TLB entries, we can use the shared caches and TLB more efficiently by reducing the duplication. And now let's look at the code access pattern of Android applications. At this point, one question we may have is, how much percentage of the total instruction footprint come from shared library? Is it important or not? And we found that shared library, it plays a very important role in the instruction footprint of Android applications. So first of all, the Android applications, they use a lot of shared libraries. Across the applications, we have tested 88 to 107 shared libraries on length, where 88 are Zygote preloaded ones. And 24 to 68 shared libraries are invoked over the course of execution, where 21 to 46 are Zygote preloaded ones. And the figure on the right, it shows the breakdown of the total instruction fetched. So the x-axis, it is the applications we have tested. We pick the popular applications from each category on the Google Play Store, including game applications, web browser, email client, calendar, video player, audio player, PDF reader, text editor, and so on and so forth. And the y-axis shows the percentage of the total instruction pages, the total instructions fetched that are from the shared libraries. On the blue bars shows the Zygote preloaded shared libraries. And the orange bars are other shared libraries, like lib chrome.so and lib adobe.so we have seen before. Yes?
If an instruction is fetched twice, it only counts once or twice in this graph?
It will count twice. It depends on the hardware performance counter.
Okay, but don't you only really care about the first time it's loaded?
So, well, not exactly. So because in the cache, if you access it twice, then it will make a difference since it's two access to the cache line. Yeah.
Does fetched here mean fetched into the iCache or fetched by the CPU's fetch execute decode loop? I mean,
Fetched by the CPU, that's what I mean.
Okay, so like percent of instructions executed, basically.
Yes. But it includes instruction on the run path by speculative execution. Like, and go back to your question, even if one instruction have seen before, but if it have been accessed multiple times, then it's harder than the other instructions.
I think this is approximation, right? Because if you have happened twice, then they are far away. Potentially, you may miss.
Right,
but I think, but it's also that it's a good approximation of instruction. Where are the hot paths?
Right.
But you kind of don't care about the hot paths of like the inner loop. I think you care about the hot paths because you're trying to improve TLB coverage and cache coverage. You really care about the paths where you're doing the virtual to physical translation, which is like from the L1 to the L2 or something like at that boundary.
Right, in that perspective, yes. And also in the paper, we have measured this in another perspective that only counted once when we have access to the same page, which is by the granularity of the instruction page. And due to time limit, I only show one figure here. But even in that figure, it's still like over 90% come from instruction footprint comes from the shared libraries.
So, are you saying like the app itself's own code is not executed that much?
So the Android applications, they're mostly the Java applications. And yes, they use the shared libraries intensively. We found that it's surprising too, because so one reason might be that the applications, they will update their versions very fast. So they want to reuse their code as many times as possible. So that is why they rely on the shared libraries.
So the shared library could be just belong to the app itself.
Yeah, like libchrome.so, although it's called a shared library, but like sometimes it's only used by one application.
The blue one are really shared across process.
Yes.
The brown one doesn't really share.
Yes, exactly. And the second question we may have is there any overlap on a shared library code accessed by different Android applications, since it directly correlates with the amount of duplicate address translation information? And we found that there's considerable overlap on the shared library code accessed by different Android applications. So for each pair of applications we tested, we calculate how much percentage of the total instruction pages accessed that are from the overlapped shared library code. And we found that on average, this number is 46%. And the overlapped Zygo preloaded shared library code, they account for 38% of the total instruction pages accessed. The figure on the right shows an example. So here, the Laya music player, it is an MP3 player application, and MX player, which is a video application. And they have 91%. The overlap shared library code accounts for 91% of the total instruction pages accessed. And Adobe Reader, although it is neither an audio player nor a video player, it still has 85% and 72% with Laya music player and MX player. So this results in a lot of duplicate address translation information in the system. Now is the time to show our techniques, starting with sharing page tables. We implement our technique on the 32-bit ARM architecture, which defines a two-level hierarchical page table. So we have a root-level page table page consisting of a bunch of entries, where each entry points to the leaf-level page table page. And here we share the leaf-level page table pages across all Android applications at fork time. So at fork time, by default, the Android process, the child process, it will request new physical pages to be its page table pages, and then copy the translation entries over from their parent process, the Zygote, to their own newly created page table pages. But by sharing page table pages instead, we make the upper level entries of the Android processes points to the existing shared page table pages of the Zygote process instead. So they don't need to encounter, so they don't need to create new page table pages. And in addition, besides the physical memory of the shared memory, now we copy and write protect the shared page table pages as well. Any modification to the shared page table page will trigger a copy and write. In particular, the following cases can trigger a copy and write on the shared page table page. Firstly, when a copy and write occurs to the underlying physical memory, then the address translation information will be changed. So a copy and write will occur to the shared page table page as well. And secondly, when a creation, destruction, or permission changes occur to a memory region within the range of a shared page table page, then a copy and write will be triggered as well. Yes?
When you do this, do you assume you know what pages are for code, what pages are for data?
Yes, we already know that. Could you please be more specific about your question?
How do you know in your previous slides? How do you know what pages in the Zygote process are for shared code? What are for the data?
I see.
Yeah.
So at fork time, in the default OS, here we use Linux, and Android is upon Linux, that it will copy the page table entry by entry from the upper level to the lower level. So when you check it, you already have the information of whether the underlying page table page is a code, is for the code or not.
It's for everything in the address space is copy and write client.
Including data.
Everything.
Yes.
Yeah.
So that's not good.
Yes, Joe, this is not her problem. Just intuitively, I would expect that for the region of memory mapped by a second level page table, it's like whatever the size of the large page is, 1 meg, 2 megs, or something
It's
like
2
that.
meg, yes.
So within that region, I would expect that very soon somebody's either going to write to a page or map something or change the permissions on a page, and you're going to end up immediately copying most of the second-level PTEs. But apparently my assumption is wrong.
So about your question, I have 2 points to make. The first one is, over the course of execution, we found that there's not so many cases that happen. Usually the mapping remain unchanged over the course of execution for the shared library, especially for the code segment. They're read and execute only, so normally they won't be changed. And for the data segment, it's read and write. And sometimes things will happen like updating a global data structure, then that will cause a copy and write. But for some shared libraries, that actually this case won't even happen for the data segment.
But the code segments are big enough that you can have megabytes and megabytes of contiguous code segment.
Yes.
Okay.
Yeah. For some shared libraries, they're pretty large, yes. And there are some small shared libraries. And here I have a second point to make, which is related to your question. So on Android, the default mapping is the code segment and the data segment of a shared library is mapped at the same leaf level page table page. So if anything changes happen to the data segment, it will trigger a copy and write on the shared page table page, making the code segment lose the opportunity of sharing page table page as well. Although it doesn't do anything, it's read and execute only. And an alternative design is to manipulate the virtual address space layout. Oh, yeah, it should be this page, sorry. We should manipulate the virtual address space layout and make the code segment and data segment mapped by 2 different leaf level page table pages by, for example, changing the linker script and force data segment to be mapped at 2 megabyte boundary. In this case, the code segment will not be affected by the modifications to the data segment. Yes?
Doesn't that have impact on the efficiency of the generated code because you need a larger displacement for all the accesses to your data?
Sorry, could you repeat your question?
So like when you have a load or a store that's accessing some global variable, for example, in the data segment, usually, and I don't know which version of the ARM instructions you're using, if you know that variable is within a certain distance from the instruction address, you can use an RIP relative load or store to access it cheaply. And by moving it much further away, you end up with bigger relocation offsets, and you need less efficient ways of encoding those instructions to fit the bigger displacement to the data. Like the code size will increase and you'll have more relocations in it as a result of doing that.
So to answer your question, when we do this change in the linker script, here the code segment, data segment, they are just between them. They're just empty.
Doesn't really change the problem. No. It's just about the virtual address delta from the PC to the data address.
I see what you're saying.
And it's that size that matters, regardless of what's in between.
So for 32-bit ARM, for 32-bit virtual address space, yes, I admit that is a waste of the virtual address space. But now we have 64-bit, so this problem is.
It doesn't matter how big the address space is. Like imagine you're using thumb instructions. I don't know what the exact issue is for ARM, but the instruction itself can talk about a data reference, and it's got a certain number of bits that it can fit in the instruction to refer to PC plus delta, and that delta is limited in the number of bits it can.
I see what you're saying.
And if the delta is small, you get a small compact instruction. If the delta is large, you need to use another register, load the immediate into the register, do an add, and then dereference, and you need all those extra instructions.
Right. So
the code size increases to enable that.
Yes, in that sense, yes, I agree that it will make a performance degrade in that sense. But we have, but by doing this, it also has some performance benefits, like that the code segment will have more opportunities of
I understand. I was just curious whether you encountered that
trade-off. Yes.
Well, couldn't you deal with that problem by just putting the code at the end of the 2 megabyte and the data at the beginning?
Sorry.
But in that figure, just move the orange code box down so it lets the data.
I see. So you're saying that how do I
need? It depends how many bits you've got, right? I don't know how it is. It goes on, but like on x86 sometimes you get like 60 bits or something. At which point, like you've got 65K, and that's not huge by comparison to a 2 megabyte.
I don't even know what the addressable
Yeah.
And the two
It's all
megabytes.
hypothetical here.
2 megabytes shouldn't be a big
Shouldn't be a
deal.
big deal.
Yeah.
And also,
You
it is
don't have that
already
many segments.
it's already what happened on default on OS like FreeBSD that they're doing this alignment enforcement. Just to, I think it's for the protection purpose that they don't want a single base page table page to map both the read and execute only and also read and write. Okay. Now let's look at sharing TLB entries. So our goal is to share the TLB entries for the Zygo preloaded share libraries code segment. And the key idea here is we leverage the global bit, which is a hardware feature that is available on common architectures like x86 and ARM. The global bit is traditionally used for the kernel mappings, which are identical across all the processes in the system. And the global bit will override the address space identifier so that all the processes, they can share the same TLB entries. And here we set the global bit in the page table entries of the preloaded share libraries code segment so that all the Android processes, they can share the same TLB entry. But there's one problem with this approach, which is there are other processes in the system that are not Android process, that are not Zygo forked Android processes, including system services and daemons. They don't have those mappings, so they shouldn't access the shared TLB entries. And how can we prevent them from accessing the TLB entries? Here we leverage 32-bit ARM's domain protection model. It is the legacy feature that is not in use by default. So by default, there are only, go ahead.
So just popping back to the previous, isn't that a problem not just for the system processes, but for any process that had inherited forked stuff from the Zygote and then you copy on wrote it and it got its own private copy of the page table?
I see what you're saying. So you're saying like those processes when they fork again?
If you've got somebody that forks from the Zygote and now they're
Yes.
sharing all the page tables,
Right.
and now they install a new memory mapping that modifies a second level page table, right?
Mm-hmm.
And so they get a copy on write copy of the page table and you create their own private second level page table.
Right.
As soon as you've done that, that process must no longer see the global TLB entries
Right,
from
right.
all the other ones.
Right.
So isn't it the case that almost every process in the system ends up having some amount of private page table state, and you have this problem appearing everywhere, not just for the system services?
So currently, whenever this case occurs, we'll prevent that process from, let's see. So when that case occurs, we can chain the page table entries. Let me show you later. So
Okay.
yeah, just it's easier to explain with the details. So I'll continue with this slide and then go back to your question. So by default, there are the ARM, the Android platform. It uses two domains, one for the user space and the other for the kernel space. But it doesn't use the other features of domain protection model. And here, and also on the hardware side, it supports 16 domains totally. So we use a new domain for the Zygo preloaded shared libraries. And the shared TLB entries, they have the global bit set, and also their domain field will be 3. And there's also a special register called Domain Access Control Register, DACR, which specify the access permission of the current process to each of the 16 domains in the system. The access permission to each domain is represented by 2 bits. And here, the non-Zygo processes, which means that all the processes that shouldn't access the shared TLB entries, their access permission to the third domain will be 00. And for the Zygo-like processes, their access permission to the third domain, including all the Android applications and the Zygote, will be 01, which means that they can access those TLB entries, but need to follow the access permission listed in the page table. And 10 and 11 have other meanings. And over the course of execution, when such a non-zygo process is trying to access a shared TLB entry, since it doesn't have access permission to the third domain, an MMU fault will be triggered and be trapped into the kernel. And inside, the trap handler will check the fault status register. And if we found that this fault is caused by a domain fault, we know that the case we are concerning about has happened, since there are no other cases that can trigger this fault, since this feature is not in use by default. And what we will do next is to flush all the TLB entries with this 14 virtual address. So when the control flow goes back to the non-zygo process, it will first encounter a TLB miss, and then the page table walk will load the correct page table entry into the TLB, and then that process can proceed. And to go back to your question, so to repeat your question, you're saying that once a copy on write occurs for any Android process, then that process will have the problem of that you cannot access the shared TLB entry.
Yeah, the problem is that you have essentially one domain that you're using to represent all the things that are inherited from the shared zygo.
Yes.
Which means all of these second level page tables that map this one view of a shared virtual address space. And as soon as a process has some, but not all of them,
yes,
it cannot benefit from this mechanism at all.
Right. So according to our experimental results, actually the copy on write doesn't happen frequently. It happens rarely to the shared page table page. So they still have the benefits of enjoying the shared TLB entries.
Okay, but
yes, but that case
as soon as any one second level page table gets copied on written, you have to treat it like one of these system processes that doesn't have access to the domain.
Right. Or you can do something extra, like using a new a domain for that. Although it's limited by the 16 domains in the system, and it's a little bit more.
One for every combination of.
Yeah, that's true.
They could also restrict the set of page tables they share, like heuristically, right?
Yeah, sure.
And just share those instead of the ones that
that can also happen, like just to share the save share page table pages. That can also happen. Yes.
So in this example, you end up flushing out the entry that has the global bit set, right?
Yes.
Are you ever going to put that entry back with the global bit, or at this point do you say, as a policy, we'll only put non-shared entries for?
So the global entry can coexist with this TLB entry of this non-zygo process. So the key idea here is just to prevent this non-zygo process from access to that global TLB entry. But for the other like Android applications, they even if these two TLB entries coexist in the TLB, because of the address space identifier, they're still going to access the global entries.
Okay, so when there's an entry for the same virtual address that has, so when there are two different entries for the same virtual address, you're saying that those can coexist, one with the global bit and one without the global bit, or? Yes,
but only for the Android processes. But the non-zygo processes cannot. Well, it can also happen when the non-zygo process is running, as long as that non-zygo process doesn't try to access that shared TLB entry.
Okay. Well, what does the processor do when there are two entries for the same address?
Yes.
I don't think so.
But wouldn't they have different assets? One's got the global bit.
Yes.
Okay, so that it does not. It uses the one specific to the asset that's.
I think that is defined on the architecture side, but I'm sorry, I don't have the exact answer on the top of my head.
Okay.
Yes.
Okay.
I have a question which is essentially similar, I think. It looks like this is giving a non-zygo process a really odd way of sort of effectively getting a side channel to look at other people, like look at what other people are putting to the TLB, right? Like now if I'm a non-zygo process, I get to see the difference between just a regular TLB walk and then this extra faulting thing, and that tells me whether other people have loaded certain things in to their address spaces.
Yes,
that
that's
I should
true.
be able to tell anything about. That troubles me a little bit, particularly since you mentioned Spectrum about people later.
Yeah, that's true. It's opened up the side channel, I agree. But I think maybe we can provide the opportunity for the application that you can indicate whether I want to share TLB entry features or not, whether I want to sacrifice security for the performance.
Aren't the non-psycho processes the system processes anyway? I think
Those are the
the
well-behaved
thread
ones.
model's the other way around.
Yeah.
Yeah, so it should be okay.
And due to the time limit, I'll only summarize some results of our evaluation. First of all, application launch. So every Android application, it follows the same launch procedure before it loads its specific Java classes. So in that way, by sharing page tables, any page table entries populated by the very first application launch for the preloaded shared libraries will be beneficial to all the following applications launched. So we found that by sharing page table, the execution time of this common launch procedure is improved by 10%. And this 10% is with mapping the code and data segment of a shared library with different page table pages. If we map it with the same leaf level page table page, then the improvement is 7% instead. And also, by sharing page tables, we speed up a zygote fork by a factor of 2.1, since instead of copying every page table entry by entry, now by sharing page tables, we only need to copy one single reference to the entire leaf level page table page. And over the course of execution, we have 38% fewer page faults for creating page table entries of file-based mapping, and 35% fewer page table pages allocated. And in addition, for sharing TLB entries, it is beneficial for Android IPC, which is very common on Android, since, for example, when the user taps on a link in an email, then the email will do IPC with the browser application. And Android use Android binder mechanisms, which involves a preloaded shared library named libbinder.so intensively. And here we create a micro benchmark in C++, where we have a server and a client process. And the client will search for the service of the server, binds to it, and invoke its specific API for a large number of times. During this process, they will use libbinder.so intensively. And we pin these two processes on the same CPU just to show the potential of sharing TLB entries. And we found that by sharing TLB entries, we can reduce the second level instruction TLB stole by 28%.
What workload did you use for this? Because a lot of these are very workload dependent on how long somebody takes to play Angry Birds before switching to another app. Where did you get the...
So we use the same applications that I have shown you before in the figure, that like including Angry Birds, Chrome, what else? The email client, and so on and so forth. So, but yes, that's true. Application launch, it depends on how you define application launch. Here we just measure the common launch procedure. But like Angry Birds, if it has a really fancy UI when you open up the application, then the launch procedure will take longer.
I guess I was thinking about the course of execution. How did you decide how long to play Angry Birds before switching to Chrome?
I see. So we have, we just do it manually, since at that time there's no automatic script to do that. So we try to do it manually, like by many times, like just play like 2 or 3 rounds of Angry Bird level 1.
So you were playing significant amounts of time.
Yeah, overnight for the paper.
Oh my god.
And only just for the
Time spent in Angry.
and just for the very first level of the game, so it's pretty miserable at that time.
So this performance savings are mainly from the shared page table or shared TLB entry. Do you measure the difference?
So the first two items, application launch and the page table, the page false page table pages, is just by sharing page table pages alone. Only the last one is the benefits of sharing TLB entries.
So when you measure the first two, you disable the shared TLB entry?
Yeah, we didn't enable it.
Okay.
Because when we enable it, we didn't see much performance improvement.
Then because the shared TLB entry has all this requirement for domain protection and other things, so even just purely sharing the page table could give you a lot of savings on performance.
Yes.
Could you make this work in a... Sorry, is this your last slide on this topic?
Yes.
Okay. Could you make this work in a scenario where you don't start out with fork, where people are like loading shared libraries and two processes happen to just load the shared library?
Yes, we do. We have a recent eSPOS paper that we implement the same sharing page table on FreeBSD, on x86. And it doesn't have this like fork parent-child relationship. It's just more that approach is more general. Like whenever two processes, they happen to use the same shared library, then we share the page table, leaf level page table page for it.
I'll ask you about it later.
Oh, okay. Okay, then I'll start with the next part. Defending against page table and last level cache side channel attacks launched by a compromised OS on a trusted execution environment. So, starting with the background, the applications always assume that the OS is secure. However, OS can be compromised by, for example, buffer overflow and information leak. And compromised OS can launch powerful side channel attacks to steal confidential application data, even on a trusted execution environment that removes OS from the trusted computing base. And a compromised OS, first of all, it can make the existing side channels worse. So, like traditional user space attacker, a compromised OS also shares architectural states with the victim, like caches and TLB, so it has clues to infer the victim's behavior and also its secret data. What is worse, compared to a user space attacker, a compromised OS has complete control over important resources, so it can control system events to reduce the noise and make the attacks easier. In addition, a compromised OS can also introduce new side channel attacks compared to a traditional user space attacker, since it has complete control over important system resources like page table. So for example, it can keep track of page table updates and page faults to infer the victim's memory access behavior. And why trusted execution environment doesn't help in this case? Although it's supposed to protect direct corruption of the OS for the confidential application data, because the fundamental architectural vulnerability is still there. The compromised OS, as well as other untrusted applications, are still sharing architectural state with the victim application. And even on trusted execution environment, the OS still has control over important system resources such as page table. So for this part of the talk, I would like to focus on defending against page table and last level cache side channel attacks launched by a compromised OS on the trusted execution environment. I'll start with reminding you of what page table and last level cache side channel attacks are. Then I'll talk about virtual ghost, a trusted execution environment that we leverage to implement our defenses. And finally, apparition, our defenses. Let's start with introduction to the page table and last level cache side channel attacks. What are they? Starting with the page table side channel attacks. So the page table side channel attacks essentially will help the compromised OS to learn the victim's memory access sequence. And by learning the memory access sequence, the attacker can infer the victim's control flow and then figure out the secret input that contributes to this control flow. And one possible implementation of the page table side channel tags is the following, that a compromised OS can invalidate all the page table entries of the victim so that every memory access of the victim will end up to be a page fault. And by keeping track of the sequence of the faulting virtual address, the compromised OS can learn the victim's memory access behavior. And existing research shows that the side channel is so powerful that it's able to recover the entire secret document. Now let's look at the last level cache side channel attacks. I'll explain it in a high level. Like other cache timing side channel attacks, there are two major mechanisms. One is flush and load, and the other one is prime and probe. Here we take flush and prime and probe as an example. So in the prime step, the attacker loads its array into the last level cache and then becomes idle. And when the victim accesses the cache line to be monitored, it will replace one of the cache line loaded by the attacker in the prime step. And in the probe step, the attacker will access the same array all over again. And if it takes longer to access one cache line, then the attacker knows that the victim must have replaced that cache line and then infer the victim's memory access behavior. And flush and reload has similar rationale. So, in order to prevent an OS from launching this page table and last level cache side channel attacks, we need to ensure three things. First of all, we need to prevent the OS from reading or writing the confidential application data itself. And secondly, besides the confidential application data, we also need to prevent the OS from reading or writing the page tables mapping the confidential application data. And thirdly, we need to prevent OS from sharing last level cache space with the confidential application data. And here we leverage a trusted execution environment called workloads to implement our defenses. Although itself cannot defend against side channel attacks, we can leverage it to implement our defenses. And you already have some features that we need. First of all, it already prevents OS from reading or writing the confidential application data itself. And secondly, it controls how OS configures page table. So in other words, the OS cannot directly write to the page table without the checking of the virtual ghost. So what exactly is virtual ghost? It is a compiler-based virtual machine that protects confidential application data from a compromised OS. It is a thin layer between the OS and the underlying hardware, translating virtual ISA to native ISA. And during this process, it can enforce various security policies by instrumentation. In particular, here it uses software fault isolation to instrument every kernel load and store to make sure that the kernel will not access the protected memory regions, which I'm going to define soon. And it also has control flow integrity to ensure that the OS kernel cannot bypass the software fault isolation instrumentation. In addition, it requires OS to invoke specific APIs provided by the virtual ghost in order to perform some privileged operations, including, for example, configuring hardware states like MMU or manipulating program states over context switch. And itself cannot defend against side channel attacks, but it can be leveraged to implement the defenses. Yes?
How does the application know it's running on virtual ghost VM and not a fake?
I see. So actually the application doesn't know. We didn't do checking on the application side. So it's transparent to the application.
Could a malicious OS pretend to be running on virtual ghost VM and convince a remote party and interacting with the enclave that it's running on good virtual gravity?
So, to be honest, virtual ghost is not my contribution, but as far as I remember, it doesn't have tracking on the application side.
You're asking, like, is there some sort of remote attestation?
Right.
Yeah, I know. You're asking whether it's like similar features like SGX that it has the tracking.
Yeah, is there a way for it to do remote attestation?
I don't remember virtual ghosts have this feature, but maybe I'm wrong.
You could presumably build it.
Yeah.
I mean, it's orthogonal to the security.
I was just wondering if it had it.
And this figure on the right shows a virtual address space layout on virtual ghost. So besides the traditional user space and kernel space, we have two protected memory regions that are not accessible to the OS. One is the secure user space, which is private to each application to save like confidential application data. And the other one is virtual ghost space, which is used by the virtual ghost itself to save internal data structures, and is exclusively used by the virtual ghost itself. Both of these memory regions are not accessible to the OS, which is ensured by the software isolation instrumentation. And now it's time to look at our defenses, apparition. It is essentially virtual ghost plus the page table and last level cache side channel defenses. Since it's built upon virtual ghost, it controls the native code generation of the OS, so it ensures that the OS is always instrumented. Now let's look at our defenses, starting with page table side channel defenses. Before I talk about the detail of the defenses, I would like to remind you of one concept, direct map, which is a contiguous virtual memory region mapping the entire physical address space as a single block. So an OS, by using this direct map, can easily translate a physical address to a virtual address by adding the offset in the traditional kernel, in the traditional OS. And the OS uses direct map to access page table. Here, our goal is to prevent OS from reading or writing the page table pages mapping the confidential application data. As I have mentioned before, that virtual ghost already configures how OS configures page table, already controls how OS configures page table. So it makes sure that the OS cannot directly write to the page table. And one more thing here we need is to prevent the OS from reading the page table pages, mapping the confidential application data. And the key idea of our method is by removing from kernel's direct map the mapping of the page table pages of the confidential application data. In other words, we're removing the mapping of the mapping from the kernel's direct map. So essentially what we do is we create a new copy of the direct map and place it in the virtual ghost space, which is exclusively used by the apparition VM. Then, over the course of execution, whenever we allocate a physical page as the page table page mapping the confidential application data, we'll remove its mapping from the kernel's direct map. In this way, since the kernel doesn't have the mappings of these page table pages, it has no ways to access those page table pages mapping the confidential application data. And also, since the apparition VM, it controls how OS configures page table, it will ensure that the OS cannot put the mappings back in its direct map. Yes?
So why do you want to prevent the kernel from reading the page table entries?
So, like one possible side channel is that a compromised OS can monitor the page table updates. For example, there are access bit and dirty bit on the page table. So it can monitor and see, okay, a write has occurred to this page. Okay, this page has been accessed. Then by gathering this information, it has clues to infer the victim's secret. Although we don't know how large the capacity of this side channels is, but still we want to close this side channel. And another side channel is the paging side channel. It is due to the fact that modern OS often uses lazy memory allocation, which means that the OS will only map a frame to a page when that page is first read or write by the application. So by keeping track of the physical memory allocation request and the mapping, it can infer the victim's memory access behavior, which is not what we want. And in order to close this, alleviate this side channel, here we did two things. First of all, we let the application VM instead of OS to manage the physical memory allocation mapping for the protected memory regions. And secondly, we disable lazy memory allocation for the protected memory regions. In other words, we map the frame to the pages of the protected memory regions upon allocation time instead of at access time. Yes?
How do you manage physical memory between the secure kernel and the regular kernel? Do you just partition it statically?
So we maintain a pool of the physical pages, which is maintained by the operation VM, the trusted code base. So it will allocate physical memory from the OS in once, and then place it in the pool, but then remove those mappings from the OS.
Okay.
And then we will allocate physical memory for the protected memory region from that pool.
And can the OS get the memory back?
It doesn't have those mappings, so it doesn't even know that those pages are there.
No, I mean just under memory pressure. What do you do under memory pressure? I mean, clearly,
I see.
If you have pressure for secure pages, you can ask the OS for more. If the OS wants more pages, what does it do?
Yeah, that's true. So currently, we don't support removing the pages from the pool back to the OS.
Okay.
So, and also, workloads encourage users to minimize the amount of protected memory region they use.
Ultimately, there's a resource management problem there that has a side channel in it. And you can push the side channel down, but it's still going to be there somewhere at that level. Yeah.
Right. We don't know the capacity of how large it is, but yes. And now let's look at last level cache side channel attacks. So the defenses. So essentially what it does is to achieve cache partitioning on the last level cache to isolate the applications needing protection from the compromised OS. We use Intel CAT, a hardware feature that divides the last level cache into subsets of smaller sensitivities, and we assign different cache partitions to the applications needing protection, the OS, and the operation VM. In particular, operation VM is responsible for configuring the cache partitioning at boot time. And also, based on the virtual instruction set it provided to the compromised OS, it makes sure that the OS cannot reconfigure the cache partitioning in the runtime. In addition, operation VM is responsible for switching to the correct cache partition depending on the code that is currently running. So for example, when a trap interrupt a system call occurs, when the control flow goes to the goes to the operation VM from the interrupted process, then the first thing operation VM will do is to switch the cache partition to be its own partition. And after it saves interrupted program states, and right before it transfers control flow to the OS trap handler or system call handler, it switches the cache partition to be the OS partition. In addition, every application needing protection will have its own last level cache partition. So we assign one cache partition for the first application needing protection scheduled. And when there are more such applications scheduled, we will divide it into multiple parts. We can divide it either evenly or according to the quality of service requests of the applications. And if there are more applications, then the number of the number of cache partitions that hardware side available, then we'll flush the cache over context switch between two different applications needing protection that use the same cache partition, so that we can ensure each application still has its private last level cache partition. And for the implementation, we use a simple approach where we statically divide the cache, the last level cache into 3 parts, and assign one cache partition to the applications needing protection, one to the OS, and one to the operation VM. On the processor we worked on, it supports 4 cache partitions totally. And the cache partitioning configuration is determined experimentally that is closest to the baseline performance. Yes?
Does CAP also cache sort of entries coming in from the page table walks and TLBs and things like this? Or is it just protecting the LLC against direct accesses?
They just protect the last level cache. And due to the time limit, I'll only summarize the results we have. So we have evaluated various benchmarks, including compute-intensive applications, network-intensive applications, and so on and so forth. And on average, the performance overhead of these 2 defenses is 1 to 18%, in addition to the overhead of virtual ghost VM itself. So the figure on the right shows an example where the x-axis is bzip2, 2 applications. One is bzip2, which compresses a 32 megabyte file, and clang, which compiles a file named gcc_smaller.c from spec CPU 2017. And the y-axis are the execution time normalized to the baseline, the stock FreeBSD. So the orange bars show the overhead of virtual ghost itself, which is 4% and 3% respectively. And the brown bars are the overhead of virtual ghost plus the page table and last level cache side channel defenses, which are 5% for both of these applications. I'll skip the detail due to the time limit. And in summary, instruction address translation overhead is already a performance problem, and we need to pay attention to it. I have demonstrated by sharing page table and TLB entries, we can help improve the code address translation efficiency of the Android applications. In addition, the compromised OS can both make the existing side channels worse and launch new side channel attacks. So since it had important system resources important system resources compared to a user space attacker, it can make the side channel attacks worse. So I have demonstrated that operation can help defend against page table and last level cache side channel attacks launched by compromised OS on the trusted execution environment with 1 to 18% overhead. And regarding the future work, for the improving code virtual to physical address translation side, I would like to, first of all, design an automatic super page promotion with dynamic heuristic. By heuristic, meaning how many physical pages are required to be resident in the physical memory for a super page region to be promoted to a super page. In a recent ISPAS paper, we have evaluated the performance benefits of various static heuristic. And I would like to come up with a design that can determine the heuristic dynamically by either tracking the access frequency to each base 4 kilobyte pages and the utilization which base physical page has been accessed within the range of a super page boundary. There is similar research on the data side, but not on the instruction side. And it would be interesting to see what would happen on the instruction side with this dynamic heuristic. And also, I would like to explore how bad this performance overhead can be in the virtualized environments. Because in the virtualized environments, it needs a two-dimensional page table. And existing research shows that it can make the current address translation overhead by increased by 5 times. I would like to see what happens to the instruction side. And the other direction that I would like to work on is the IO-MMU. Are there any side channel attacks that can be launched by the OS on the IO-MMU? So is it possible by keeping track of the page faults, like what happens with the traditional MMU? And if so, how can we do to prevent against it? Can we leverage a trusted execution environment like Virtual Ghost to prevent this from happening? That is also one interesting direction that I would like to see. And thanks to my collaborators, I greatly appreciate their guidance and collaboration. So this is the end of my talk. I'll be happy to take any questions. Thank you so much for your attention. Yes.
So did you consider using a hypervisor instead of using Virtual Ghost?
So, so in the regional paper Virtual Ghost, it does compare performance with the hypervisor.
Okay.
And with hypervisor approach, like, sorry, I forgot the name. I think it's engines, but it doesn't matter. That it can incur a smaller overhead than the hypervisor approach, since you don't need to go through additional layer.
Do you think there's anything fundamentally different about side channel defenses for something like Virtual Ghost than SGX or Trust Zone?
Fundamental different. Could you be more specific, please? So, like,
I don't know. I mean, it seems like the resources you're trying to protect are very similar. There's the
yes.
cache, side channel, and
right, and
page table access,
yes.
those kinds of things. The resources are very similar. The trust model is quite similar. The OS is kind of managing resources, but then there's this more trusted thing on the side that's like a reference monitor. So conceptually, it seems like basically the same problem. I wonder if there's, if you can contrast it in any way with all the work on side channel defenses on SGX, for example.
I see. Yeah, conceptually, we try to solve the same problem because it exists in both architectures, but among both platforms. And are there any difference? So SGX uses the hardware side support, but Virtual Ghost is more like the compiler, the software approach with existing hardware support. I don't have a very good answer at this moment. But so, for example, regarding the address translation side, the Intel SGX its environment is to ensure that the illegal translation will not appear in the TLB. But on the Virtual Ghost side, it doesn't have the hardware side support. So in the software fault, you use the software fault isolation to make sure that the kernel cannot perform any illegal operations. So that maybe lead to some difference in terms of the side channel.
Probably makes it easier because you have more software in the path that you have control over.
Yeah, I think it's an open question too. That on the SGX side, you use more hardware. Sorry that I don't have a very good answer at this moment.
I assume you can on the software control class, you control all the things perfectly.
Yes.
Yeah.
It makes it easier.
you so much for your attention.